this idea of a determinant came before the other one. So we're going to do right down diagonals. So minus 1 by k by minus 2 is plus 2k. 2 by 3 by 4 is 6 by 4 is 24. And 4 by k by 4, 4 by 4 is 16 by k is 16k. That's the right down diagonals. Minus left down diagonals. 2 by k by minus 2, minus 1 by 3 by 4, 4 by k by 4. So 2 by k by minus 2 gives minus 4k. The next one is minus 1 by 3 by 4 is minus 12. And the last one is 4 by 4 is 16 by k is 16k. Now you just need to be careful with the signs here. And of course this k has nothing to do with k hat. This is a variable. Probably a bad choice of name for a name. So I see 18k minus 12k, which is that 6k. So 18k minus 12k is 6k, and 24 minus 12 is 24, plus 12 is 36. The determinant of this matrix is 6k plus 36, and if we want this to be not invertible, this has to equal 0. And this is what I mean by, this would be more like the equation that if I examine this, you end up with an easier kind of a job. Take the 36 away from both sides. Divide both sides by 6. So just when k is equal to minus 6, every other value of k, it's inverted. Any question on this? So this is the kind of question. So you could be asked something like this. You could be just given a 3 by 3 and said, is it invertible or not? And you'd have to calculate the determinant. If the determinant is 0, it's not invertible. If the determinant is non-zero, you can invert it. Right. Okay. So now we're going to give you something that's kind of useful, a little bit useful, depending on where you go. So we're jumping. Actually, we're just going to the next page. Right. Something called Kramer's rule. Now, I won't give the big spiel. If you want to get the spiel, they're in the notes. But if you ever have simultaneous equations, there's sometimes you might only be interested in one of the variables. Why? I don't necessarily. I can't think. Well, the one example I think of is maybe electrical. If you have an electrical, some kind of a circuit. Now, I appreciate you don't do electrical circuits, but maybe something like this. We have a current here, a current here, and a current here, and maybe there's some kind of a device here. Now I've drawn a resistor, but some kind of device. And you just have to make sure that the current isn't too big here. So if you write down the electrical laws here, you get simultaneous equations in the three currents: current 1, current 2, current 3. And maybe rather than finding all of the solutions, maybe you just want to find one of them. And that's what Kramer's rule can do. The other thing it can do is, or not that it can do, but it's useful for, is if you have, so they're simultaneous equations, but these 2 by 2 simultaneous equations, if all the numbers are decimals, it's very nasty to do the way you would have done it before. This Kramer's rule is very, very good if the numbers are nasty and you have decimals. And that's the only time you use this thing. You can have simultaneous equations in more unknowns than 3, like 4, 5, 6, 7, 8, you can have loads. But the honest truth is that Kramer's rule is only useful in those two scenarios. you might say, well, why are we doing it so? Well, I think it is useful for these when these numbers are decimals. So well, I won't go back, but you could just end up writing down some little equation with forces, and because there's sines and cosines involved, these are messy numbers. Kramer's rule is good in that case. Okay. Right. So remember that from last week, if you have simultaneous equations, you can write them as a matrix equation. So for example, this by x plus this by y plus this by z equals this, and this by x plus this by y by this by z equal to that. This by x plus this by y plus this times z is equal to that. It can be written as a matrix equation. So I might write it as, say, AV equal to B. And I think in this chapter anyway, whenever you see these simultaneous equations, that's what we'll do. We'll do it down here in a minute. Then what Kramer's rule does is it actually gives you a formula for finding one of them. Now you might say, why don't we find all of them like that? Say if you wanted to solve a trick, why don't I just do Kramer's rule for this, Kramer's rule for that, Kramer's rule for that? Well, the problem is you have to calculate determinants, and to do a 3 by 3 system you have to find 4 of these, which is it's a bit long. And then if you go up to 4 by 4, you have to find 80 of them. And you say, okay, a computer can do that. If you go up to a 5 by 5, big number, and even a 10 by 10, a computer can't even do it. So it seems like it's a good technique, but actually it's crap. It's good for 3 by 3, and it's good for 2 by 2 with decimals. Now, to explain how it works, probably the best way is just to do examples and then go back. Okay, so first thing we'll do is we will write these things as matrix equations. So this thing is the same as a matrix equation: 4x, 5y, 1x. What's the coefficient of y in the second equation? Not 1. Minus 1. Minus 1 times xy equal the constants 8, 11. Now, so let me be clear. You can be asked to solve this using the inverse matrix method, which is a daft way of solving simultaneous equations. It just allows you to show me that you know what inverses are and you know how to work with them. But if these are decimals, this Kramer's rule is actually useful. Okay. Now here are not, so this is a stupid example. But anyway, so this is where we are. So what Kramer's rule does, it does this weird formula: x is dx over d. Now what dx is, well, actually d is easier. So d is the determinant of this matrix. So this is Kramer's rule, so it's dx over d, but you need to know what it means. D means the determinant of the matrix coefficients. Now what dx is, essentially, you take the constants and you put them in here instead of the x coefficients. Now you say to me, why does that work? And I have to say, it's one of the questions I can't actually answer. I've never gone through the thing, but it does work. You trust other people that this works? I trust them. You trust. This is going to work? You believe this? Yeah, okay. So dx, what you do is it's the same thing, but instead of the x coefficients, you put in the constants. So instead of 4 and 1, you put in 8 and 11. The other bits the same. is it. And now you just do your right down diagonals minus left down diagonals. So do 8 by minus 1 is minus 8. Take away 5 by 11 is 55. And then 4 by minus 1 is minus 4. Take away 5 by 1 is 5. So I get minus 63 over minus 9, which is equal to plus 7. And I'm saying, for sure, this is good if these numbers are all decimals. Okay, now we'll show how the other one works similarly. So for dy, you take the constants and you put them in instead of the y coefficients. Essentially, that's what dy is. So we get, now the d is the same, the thing on the bottom is the same, it's just minus 9. And dy is this thing, the 4, 1, 5 minus 1. Shit. But you replace the y coefficients with the constants, the 8 and the 11. Sorry. So replace the x coefficients for dx, replace the y coefficients for dy. And you do the same crack again, right down diagonals minus left down diagonals. 4 by 11 is 44, minus 8 by 1 is 8, over minus 9, and that gives 36 over minus 9, which is equal to minus 4. And then obviously in an exam situation you can just check your answer. So 4 times x is 28, plus 5 times minus 4 is minus 20. 28 minus 20 is equal to 8. Yeah, that works. And check the other one as well. X is 7 minus 4. 7 plus 4 is 11, so that works. Any questions on this? No? Okay. So the other formulas for 3 by 3, we will do examples, they work similarly. Except you've got, well, again, we're better off just see it with an example. So this is all the spiel, I won't go through that. So it's basically just saying that it seems like it's great, it's not actually that great. It's only good for 3 by 3s where you want to find one of them, but it is good for decimals. Okay. So we'll have a look at this question. Now this question, similarly to, I think we did something similar where you have to form the equations yourself. So let's look at this question. So Rafael, whenever an exchange student from Brazil made phone calls within Ireland to the United States and to Brazil, the rates per minute for these calls vary for different countries, but the total call duration for each country is known. Okay. So 19 minutes of calls within Ireland, 120 in America, 180 in Brazil, and the bill is 252. Okay. Clearly define 3 unknowns x, y, and z. We'll get back to that. Write down 3 equations in x, y, and z to form linear systems, simultaneous equations. Write the linear system as a matrix equation. Okay. If ax is equal to b, write x in terms of a and b. We'll get to that. And then at the very end, use Cramer's rule or another matrix method. You don't have any other ones because you don't know how to find the inverse of a 3 by 3. Find the rate per minute for calls to Brazil. So our issue is, what the hell are the unknowns here? Price per minute, yeah. So maybe with that XB, we'll say Ireland, I'll say rate instead of price per minute, just listening. So the Ireland rate, let Y be the USA rate, and Z be the Brazil rate. write down 3 equations in x, y, and z to form a linear system. So, again, we'll just do something similar here. Well, number of minutes, rate. So, well, the number of minutes, say we're looking at the Ireland 90. So this is something, I think it's difficult. So I will just start with 1 cent, 2 cents, 3 cents, X cents. So 90 minutes, 1 cent per minute, what is the bill? Uh-huh. 90 minutes at a rate of 1 cent per minute, what's the bill?
130.
130. Are you doing the whole thing here? Just this bit. It's not, okay, I think there's a little bit of confusion. This is minutes and this is per minute. Like this is an hour and a half, that's fair enough. But it's 1 cent per minute. What is it? 0.9. It's just 90 by 0.01. What's the bill here? 90 by 0.02, 90 by 0.03, so the minute by the rate per minute. So this one, when the rate is unknown, is going to be 90x. So the bill for Ireland here is 90x, plus the bill for USA is 120y, plus the bill for Brazil 180z is equal to the final bill 252. Okay. So we'll write the 3 equations down. So we get 90x plus 120y plus 180z is equal to 252. So first, second one is 70x plus 100y plus 120z is equal to 184. 50x plus 110y plus 150z is equal to 206. Now there's an idea here that you divide both sides of all the equations. We'll even go for 100. The reason is because we're going to be multiplying along diagonals. Say roughly you'll have 100 by 100 by 100, which is a million. You don't really want numbers that big, so you can always divide both sides of an equation. So we'll divide everything, both sides of this by 100, divide both sides of this by 100, and both sides of this by 100. And Kramer's rule isn't particularly worse with decimals. So you're getting 0.9x, you don't have to do this, but it's a good idea, plus 1.2y plus 1.8z equal to 2.52. Uh, 0.7x plus 1y plus 1.2z equal to 1.84, and finally 0.5x plus 1.1y plus 1.5z equals 2.06. Simultaneous equations and 3 unknowns. You're more likely to see this with forces or something like that, or a little later curve fitting, or there's other things you'll see it as well, the more I'm apt to do simultaneous equations. So that's part B. B said write down 3 equations in x, y, z to form a linear system. That's that done. Next bit, write this as a matrix equation. It's asking for ax equal to b. So same crack again. So the A would be the 0.9. Just take the coefficients, 1.2, 1.8, 0.7, 1, 1.2, 0.5, 1.1, 1.5, that's the A. The X is the XYZ, the vector of unknowns, equal to B, which is the constants here. So this is AX equal to B. So let's just show that you understand, or that you can write simultaneous equations as a matrix equation. Now the next thing is a bit trickier unprompted. If AX is equal to B, write X in terms of A and B. So starting with AX